let's get started. I think I will assign another homework today. So without homework, I think it's hard for you to really or truly understand these abstract things. But I want to emphasize the probability is very useful, not only for control, it's actually for many other fields, including robotics and machine learning. So I think the thing we reviewed in this class for probability will be helpful for you to understand other class or even understand the literature. Will be very helpful for that as well. And so let's quickly recall what we have learned last week. I think we finally started deriving Kalman filter. But before deriving Kalman filter, we spent a lot of time reviewing probability, basic probability. And there's only a few things I want you to kind of remember. First of all, what does Kalman filter do? In terms of its functionality, it's nothing but try to estimate the system state given the system input and output data. Okay, that's the very first thing. It does the same thing as the Lundberg observer or any kind of observer, but it just takes a probabilistic or stochastic view of the system behavior. Okay, and I also told you that without any proof, I told you Kalman filter is nothing but compute conditional mean. All right, but we start to see why that's the case because last week we finally reached to the fundamental theorem of estimation, which is what? What's estimation problem, by the way? You want to use measurement from y, which you can measure, to estimate some hidden variable, which you cannot directly measure, which is x, right? There's many ways you can do this estimation. And of course, some of them are good, some of them are bad. But if we agree upon a common criteria, which is called mean squared error, then the best estimator or estimate, or the so-called minimum mean squared estimate, is given by the conditional expectation. Okay, we show you why that's the case, and there's a proofs you can check. So whenever you want to estimate something based on other measurement, okay, if you want to just do the best minimum mean square estimate, simply you just need to compute the conditional expectation, right? That's why conditional expectation is so important. And that's why we spend a lot of time reviewing the concept of expectation and conditional expectation. And so Kalman filter is nothing but compute conditional expectation because we want the minimum mean square estimate of the state given the input-output data pairs, okay? As I mentioned last time, it's very hard, although conceptually or analytically, it's easy to write down the formula, conditional expectation, this one, right? But how to compute it is very hard if the dimension of the state and the input-output data are large. Okay, so I don't think we can do that in general, but a very special case for which we have analytical form for conditional expectation is Gaussian. Okay, that's why Gaussian is very important. So we spent some time to discuss Gaussian random variables, Gaussian random vectors. Okay, how to check whether a given random vector is Gaussian or not. Yeah, Shuyan. How to check whether a random vector is Gaussian or not? By definition. Okay? What's the definition of Gaussian random vector? It's PDF, probability density function of this form. Okay? Whenever you can write a PDF like this form, it's a Gaussian. If not, it's not. Right? As simple as that. Okay. But Gaussian random vector has so many nice properties you have to remember or you have to know. And there's three things that I want you to remember, at least, before the end of this class, at least. There's three facts. Okay, the reason I call them fact is that I don't prove that for you. I want you to somehow kind of believe me, all right? So typically I'm okay. I'm bad on calculating the numbers, but these conceptual things I'm okay, right? So believe me, fact one, uncorrelation or uncorrelated Gaussian means independent. But an independent also implies uncorrelation as well, right? But for Gaussian, you can go both directions. But for general random vectors, you can only go from the independent to uncorrelation, not the other way, all right? The second is very important thing is linear transformation of Gaussian are Gaussian. Okay, if I have a jointly Gaussian random vectors, or you just have a Gaussian random vector, then linear transformation of this random vector will be Gaussian. And we know how to compute the mean and the covariance for this linear transformed Gaussian, right? The third one I put a lot of kind of emphasize here is the conditional Gaussian is Gaussian. Okay, so how should we, let me see whether I have other ways to explain that. Yes, okay, no, where is it? Conditional Gaussian is here. Okay, conditional Gaussian is that I have x and y are jointly Gaussian. Jointly Gaussian means if we put them together as an overall random vector, that random vector is a Gaussian random vector. Okay, if that's the case, then x conditional on y taking some small y values is also a Gaussian. How should we understand this? Xiaohan, how should we understand this? Given y equal to y, there's only a few kind of sentences I summarize for you. You need to memorize, okay? Not for English, just for the way you approach the problem. Given capital Y equal to small y, x is still random. It's not completely specified, right? And that randomness has a density. It turns out that density is a Gaussian. As Yuntian said, it doesn't need to check the density, right? It turns out that density is also a Gaussian. So that's why conditional Gaussian is Gaussian. And the formula is given by these two things. Gaussian random vector is characterized by two parameters, okay? One is mean, the other one is variance or covariance matrix. Okay, if you talk about Gaussian random vector, we have a covariance matrix. Okay, each of them, if I gave you the y value fixed, then each of them have a formula. I explain what this formula means. Okay, so I think last time we finished this example, right? Let's do another one. All the Kalman filter, I'm doing this derivation now. It's just the key elements in deriving Kalman filter. Okay, if you understand those simple examples, we put them together, that become the full derivation and the whole story about Kalman filter. Okay, let's look at this example first. Suppose I have a z random variables. Okay, I say z is distributed according to a Gaussian. Shuyan, is this Gaussian? Yes, right, I told you it's Gaussian, right? What's the mean? What's the dimension of this Gaussian random vector? 3, right? This is Gaussian in R3, and this is the covariance matrix. Now I'm going to ask you one thing, how to read this matrix. What does this mean, this number? 0.5 means covariance of Z2 with Z3, okay? Each of this number is a covariance between certain components of the random vector. Okay, so you know everything about this random vector. Now I'm going to ask you, this is a random vector. Then I say, let's define that P, I define another random vector, okay? P is Z1, Z3, okay? Can I do this? Of course. I only pick the first and third element of this vector, and I call Q equal to Z2. Okay, so I want you to find expectation of P given Q, I say Q equal to 3. Oh, I want to find the conditional expectation, okay? So again, conditional expectation is the key for understanding common filtration. To understand this, given Q is 3, P is still random, right? And I want to know that distribution of that randomness so that I can compute its expectation. Okay, so how do we do it? First of all, is P, Q jointly Gaussian? Why? So if joint Gaussian means I need to put PQ, that will be a Gaussian. Is this Gaussian? That's Z1, Z3, Z2 is this Gaussian. Why? It's a linear transformation of Z, right? So no matter how I arrange the coordinates, it will be Gaussian, right? So that will be 1, 0, 0, 0, 0, 1, 0, 1, 0 times Z. Okay, that's a Gaussian. Are we with me? Okay, if we're in the Gaussian world, everything is simple. Because conditional Gaussian, it's Gaussian. So I will say, if I write like this, P given Q equal to 3, this whole thing, if I write like this, how do you understand this thing? It's a random vector, or of course, we can call it random vector, either way is fine. It's two-dimensional random vector. Because P, the thing matters is P, all right? P is two-dimensional. P is a two-dimensional random vector. Its distribution is specified by the original P given Q equal to 3. So Q given equal to 3, P is still random. That randomness is a Gaussian, and it's two-dimensional Gaussian. And by the formula, we know this two-dimensional Gaussian given Q equal to 3. What's its formula? Of course, by definition, but we have a formula now. You have to start. For Gaussian, we have a formula. So the mean is unconditioned mean, all right, plus covariance of PQ, covariance of Q inverse times surprise. What are the surprise? So we see 3, but we expect E of Q is what? Is 5. So on average, it's 5. But it surprised me a little bit. It's only C3. It's below its expectation, right? But then I need to normalize it by how noisy that observation is. Because the more noisy the less trust, it's less reliable that measurement is, right? So then that is how correlated these two things are. Then this thing will give you a correction, okay? So let's see. So overall, I think it's just plug in the formula. EP, what is the EP? Minus 1, 4, okay? What about covariance PQ? So covariance P and Q is covariance Z1 with Z2 and the covariance Z3 with Z2. Okay, it's 2 by 1. So in the exam or in whatever test, if the dimension is wrong, I think I would just give you almost 0. If the number are wrong, dimensions are right, you almost get the full mark. So of course you need to be, if there's involved some calculation, you make calculations wrong, that's fine. Okay, so this will be Z1, Z2, you know how to read this, right? This is -1, Z3, Z2, this raised to is 0.5. Okay, so this guy is minus 1.5. Covariance Q is what? It's this guy. So it's 1 over 4. So we don't need to do an inverse matrix. It's just the inverse of a number, and times the minus 2. Okay. Overall, I will get, I think it's negative half, and 15 divided by 4. So is that clear? How to compute conditional expectation for Gaussians? If this is clear, you are 90% there towards fully understanding. Well, no, sorry. In terms of content, yes, it's almost 90%. But in terms of hardness, or the most challenging part, we haven't seen it yet. It's maybe still quite a lot, all right? We're going to fix that today. So this is the conditional expectation. Okay, I have another example. I think you now start getting almost bored by those kind of examples. I mean, I'm gradually somehow warm you up for the more intense derivations. So this one has more meaning, okay? I have X, a two-dimensional Gaussian random vector with mean this and the covariance that. I have Y defined as a matrix times X plus V. V is another noise. It's another Gaussian random vector. The thing that I have for you is I know V is independent of Y. Now I ask you to compute the minimum mean square estimate of X given Y equal to 1 and 1. All right. First of all, what do we need to compute? The minimum mean square estimate of X given Y equal to 1 and 1. What does it mean? So you see a observation Y equal to 1 and 1, and you want to find the best guess for X. You don't know it, right? If you didn't take this class, the best guess for you would be, I will ignore the noise. I will invert this matrix. I can find X. Okay, that's one heuristic way to do it, right? And the way we are trying to do it is the optimal. Okay, it's the minimum mean squared error of X given Y. So what's by fundamental theorem? We know the minimum mean square estimate of X given Y equal to 1 and 1, so what is it? Conditional expectation, all right? Although I didn't ask you to directly compute the conditional expectation, I want you to find the best estimate. That's conditional expectation. So all we need to do to solve this estimation problem is to compute this conditional expectation. Now the second step is that, okay, how do we know how to compute this? First of all, you need to know the density of X given Y, right? It's typically hard, but in this case, we will try whether they are Gaussian or not, okay? The first question I will ask you, Y and X are jointly Gaussian? I'm asking you, okay? I'm not stating this fact. It's a question mark. Are they jointly Gaussian? The reasoning goes like the follows. Okay, typically I don't test this kind of reasoning, but I want to tell you the full story. So I know X is Gaussian, all right? I know V is Gaussian, okay? I know X independent of V, that's important, okay? If both of them are Gaussian, they may not be jointly Gaussian. I mentioned that last time, but I didn't prove it. I will give you a counter example in the Blackboard. Okay, I'll upload the counter example. I can create many counter examples. I just don't want to go through them in class. But if they are independent, then the claim I can make is X and V is jointly Gaussian. So the whole vector is Gaussian. Are you with me? The direct consequence of these three is I can only say X and V is jointly Gaussian. I cannot say other things, all right? But Y is a linear transformation of X and V. So Y is Gaussian. I can only say Y is Gaussian. Now I will ask you whether Y and X are jointly Gaussian or not. So what I really want is I want to see whether the whole vector is Gaussian or not. Are you with me? Yeah, it's still a linear transformation. Great. So it will be identity 0, X and V. This is A identity, right? I will call this guy A, all right? I'll call this 1, 0, 1, 4 A matrix. I will call this guy A matrix. So I will say linear transformation of Gaussian, it's Gaussian, so X and V, Y. So I'll call this Gaussian, which means X and Y jointly Gaussian. I think this kind of notation is incorrect or is not precise. So I will say X and Y are jointly Gaussian. That means the whole vector is a Gaussian random vector. Okay. Now we are in the Gaussian world, then everything becomes simple, right? So I will say the minimum mean square estimate, I'll call that hat, of X. It's conditional expectation of X given Y equal to 1 and 1. Now we plug in formula, right? The part you like the most is you have some formula to plug in and calculate some numbers. Without any thinking, you can get some marks, right? You get some credits. So that will be expectation of X plus covariance of X with Y times covariance of Y inverse times surprise, 1, 1 minus expectation of Y. Okay? Now I want to ask you how to compute those terms. So maybe I know EX, right? What is EX? Let's call it, let's say EX. What is EX? Oh, EX is given. EX is 4 and 4. Okay? Let's say 3.2. Now I want to compute, let's first compute covariance of X and Y. Okay, this term. So how do we compute it? Let's write down by definition, right? So you plug in X, Y is defined. I didn't tell you what Y is. Y is defined indirectly through X and V, right? So that will be AX plus V. Okay, so then I can compute, right? By the properties of covariance, which is just the property of multiplication, okay? So I know this is the covariance of AX plus covariance of XV. Okay, and I know this is covariance of X with itself, A transpose, right? I move it. Okay, what about covariance of this? 0. Why? Okay, if X and V are independent, covariance has to be 0. That has nothing to do whether these two vectors are Gaussian or not. You see what I mean? I encourage you to prove this by yourself. It's super simple. Oh, I already did this, right? Okay, so then I don't want you to do that again. Okay? Or at least you can prove it now, okay? Because the independence means the factorization of densities, then covariance becomes 0, okay? So, well, you can check our previous slides, maybe. I forgot we proved it before. Anyway, this is 0, all right? So overall, I will have, what is it? Covariance of x with x just means covariance x, right? That's this guy. Okay, that's 4, 1, 1, 2. A transpose is 1, 1, 0, 4. Overall, I will have 5, 4, 3, 8. A transpose, I got it wrong. What is A? Okay, A transpose, sorry. 1, 1, 0, 4, okay? So overall I have, this is a 5, this is, this is a 4, sorry. 4, 8, 1, 9. Is that 9? 9, okay. Good. I don't care. So anyway, so up to here, my job is done. After there, the calculator does it, or AI does it. The only thing you are better than AI is from here to here. After that, I think everyone is worse than the computer, okay? 3.3. One more thing is we need to compute covariance of y, because we need to do the inverse. So covariance of y is ax plus v, ax plus v, all right? So I will have covariance of ax with ax. That's almost like multiplying these two terms. Covariance of ax with v plus covariance of v with ax plus covariance of v with v. You should be very familiar with covariance properties. It's not really properties, it's a multiplication of these two sums. Because covariance is multiplication of the two terms, okay? So this guy is A covariance of x, A transpose, plus this is A times 0, okay? Plus this guy is 0 as well. Those zeros are matrix 0. All right, it's everything is 0. And is this guy 0? No. Why not? It's noise. Expectation is 0, covariance is not 0. Okay, otherwise it's not random variables anymore. So this is, what's the covariance of V and V? Identity, right? So I told you, so that's 1, 0, 0, 1. So overall, I think I will have something that I don't care, right? You know, this guy. You should care, right? So during class, I don't need to care about those calculations. So overall, I should say you can check the MMSE based on this formula. Then I know everything, right? Do I know everything? Oh, I need to know expectation of y, right? So let's say expectation, that's 3.4 EY is very simple. It's A times EX plus EV. EV is 0. So A times EX, which is 4 and 20. I think that should be correct. 4 and 20. Okay, overall I have everything I need. So this will be something you can check. 44.1136. I don't believe my calculation, so that number doesn't have any. Anyway, I think you know how to compute, that's fine. That's how I can calculate it. I may be wrong, but just for your ref. All right, you got it. Now you know how to compute the minimum mean squared estimate of something. Some hidden variable given other measurable measurement data. Okay. Any questions so far? Now we have everything. Let's go back to our key things, which is the Kalman filter. Let me define a few notations a little bit more carefully. I think you have seen this format many times so far, but we haven't explained in detail what are these means. Any questions? Huh? Similar? Gaussian? Oh, jointly Gaussian. I think this lecture we have it, right? Did we do it? Let me remind you. It's not. See that, okay? Jointly Gaussian, by definition, is a triangle means definition. This is as a whole vector, x, y is a Gaussian. So I can have two Gaussians, but Gaussian means the marginals. So these two marginals, fx, are Gaussian density, fy is Gaussian density. But that doesn't mean the joint is Gaussian. All right? Not unless, one special case is that if these two are independent, then the joint will be directly, this multiplied together, they will be Gaussian. Okay? You can check that very easily. By the way, you just multiply these two, you find out this is a two-dimensional Gaussian with diagonal coercion matrix. All right. No, it's just we put them together as a whole vector is Gaussian. No, let's do this way, okay? This jointly Gaussian, by definition, means, by another definition, sorry, more explicit. This can go this way. It's just x, y, this is Gaussian. You see what I mean? This thing is a Gaussian, jointly Gaussian, right? This joint distribution is Gaussian distribution. That also means if I put them together as a whole vector, that whole vector is Gaussian. All right? Because in this class, the only thing that I ask you to somehow get yourself familiar with is that every of these things may be vector, all right? In your introductory random variable class, I think by default, everything is scalar. Here, by default, it's vector. So this could be three-dimensional. This could be two-dimensional, right? What I want is the five-dimensional thing is a Gaussian, all right? If these two are independent, you multiply them together, it will be Gaussian. You can check that. That'd be very simple to see, all right? Great. Any other questions, by the way? We should clarify those questions before we move on, right? All right, now let's talk about this Kalman filter setup. There's many variations of Kalman filter. Okay, there's extended Kalman filter. I think we will cover that as well, maybe next lecture. And there's the ensemble Kalman filter and scientific Kalman filter. There's so many different versions of Kalman filter. But the most fundamental one, the basic version is this, okay? So as I mentioned before, the system is still linear, but is the system linear or not? Depending on how we define linearity. So it's a linear or affine in state, affine in control, right? It just have some perturbations of the noise, which this guy is called process noise, and it's Gaussian. Okay, and this guy is called measurement noise. So the measurement is not clean, can have some noise, and you know some noise random distributions, which is also a Gaussian. Okay, it's zero mean, and it's also has a distribution, all right? My notation is similar. I think, let me see. I think typically I don't do this, right? I think this should be P dimension, right? This should be M dimension, right? That's the input dimension is M, state dimension is N, output dimension is P, okay? So now I'm going to ask you, what's the dimension of this covariance matrix? Or what's the dimension of this guy? This is the P, the same dimension as Y, right? So this is a P-dimensional Gaussian with 0 mean and some covariance matrix. And the process noise is Rn, so it's n-dimensional Gaussian random vectors. All right, so it's just start, and also the initial distribution you also don't know exactly. Okay, you have a expected value mu0, and you have some covariance matrix capital Phi of 0. Right. The assumption is that the initial state is independent of all the process noise for all k. This means for all k. And x0 is also independent of the measurement noise, and the measurement noise and the process noise are also mutually independent for all k. Under these assumptions, I'm not sure how much you can get out of these assumptions. I would say that here, A, B, C, D matrix. Here I say A, B, C, D matrix, C, K, D, K. I put it in a more general form because K can be dependent on, A, B, C, D matrix are deterministic, but they can depend on K. They can change over time. Okay, in this particular setup. Those are all deterministic. What deterministic mean again? Single valued. I may not tell you those numbers, but you know eventually you will have some number there. It's not like a random, which has multiple values, and each of them has different kind of probability density or mass distribution. Okay, these are deterministic. Okay, let's do one step. I assume initial state is not completely known. Okay, it has distribution. If you know that for sure, then of course you can make this covariance very, very, very small. That's fine. Okay. So now I'm asking you, what about x1? X1 is Gaussian or not? I know x0 is Gaussian, right? According to my modeling assumption, is x1 Gaussian or not? Oh, by the way, there's another thing. UK is deterministic as well. Okay? UK is something you send to the input. You send to whatever input you have. Okay, so it's deterministic. Okay, so this guy is deterministic. That means this guy is a number. All right, and x0, so x1, so x1 is a1. A0, x0 plus b0, u0 plus w0 or omega 0. Okay, so this is Gaussian. This is a number. This is Gaussian as well, right? I have a summation of two Gaussians. Is this Gaussian? Only when omega 0 and x0 are independent, I know for sure it will be Gaussian, right? It's the same thing like what this example says, all right? This is two Gaussian summing together, but you need to assume they are jointly Gaussian before you can move on, right? That's why we have those assumptions. You know, mathematicians are really, really serious about everything they put on the paper. So all these assumptions has a meaning, you need those, each of these to make sure everything is Gaussian. Okay, so X is Gaussian, omega 0 is Gaussian, x0 independent of omega 0. Overall, you will say x0 omega 0 is Gaussian. okay? And then you know x1 is Gaussian because x1 is a linear combination of Gaussian, right? This Gaussian. Similarly, I can derive y1 or y0 is Gaussian. So overall, implications of these assumptions, I hope you can believe me, I also encourage you to go over them. Check x1, y1, x2, y2. Check a little bit, you will see what you need to guarantee everything is Gaussian. So Kalman filter essentially lives in the Gaussian world, okay? xk is Gaussian, yk is Gaussian for all k bigger or equal to 1, and everything is jointly Gaussian. I would say, let's assume, okay, everything I mean xk with yk, xk with yk minus 1, all of those things are, everything is jointly Gaussian. We don't need to check like this anymore, okay? That would take a lot of effort. Let's believe all the variables you see, they're jointly Gaussian, okay? If you don't feel comfortable, you can check a little bit by yourself. I think you'll have all the tools you need to check those things. All right, so another symbol that we introduce is the capital Y. Capital Y is the measurement history, okay? From Y0 up to YK. So capital YK is all the measurement you received, collected up to time k. So this vector will grow bigger and bigger as time goes on. Okay. So we're in the Gaussian world. That's the modern assumption. What we're trying to do, remember what Kalman filter trying to do? UK, YK, I want to find XK hat. That's what Kalman filter tried to do, all right? But we are living in the probabilistic world now, and we want to make sure what we estimate is the best according to mean squared error. So state estimation problem, or the problem we care about, is find the minimum mean square estimate of xk given capital YK. Of course, also given, that doesn't matter, also given all the u's, okay, u0 all the way to uk minus 1. All right, those are deterministic things. Those we don't need to given or not, but that's you know that, okay? So the solution, Zhuyan, by fundamental theorem, the best estimate of xk given yk is what? Conditional expectation, right? It's this guy, all right? So all we need is that, okay? So Kalman filter, but compute this guy. You should have a high-level understanding of what they're trying to do. Then everything else is details, right? The devils are in the detail. The details are important, but the most important thing is know what we're doing. Otherwise, all the derivation may make sense, but they don't just come together. They just fall apart, all right? So all we are trying to do is to compute conditional expectation. Okay, I somehow repeat this many times, but now you see more clearly about this statement. Well, let's prove how we can do this in a recursive way. It's very simple. There's one step that takes some effort to understand. All the other steps you already know. Okay. So let's introduce a few notations you often see from the literature. My notation may be a little bit different from some existing books or literature, but should be consistent with most. All right. Let me define some notations. All of these has derivation. So x hat in the context of Kalman filter is always means the best. So it's the minimum mean squared estimate. Okay, that hat. A hat means sometimes denote estimate, not the true value, right? But you can have very stupid estimate. So in this context, x hat always means the best estimate. Okay, the minimum mean square estimate. And here is the x hat of k, given k means the best estimate of xk given measurement up to time k is this guy. All right, and xk hat k minus 1 is the best estimate of xk given yk minus 1. That's definition. Can I have this? Xk given k plus 2. By my notation, yes. Can I have this? Mathematically, yes. Practically, also yes. If you know the measurement up to, by definition, this means, I want you to make sure you can generalize my notation. This is k plus 2. That's what I mean, right? So that means the best estimate given measurement up to k plus 2, the best estimate of xk given measurement up to k plus 2. So you have somehow not only to time k, but you have two more measurement coming in before you make the estimate of xk. You could have that, especially you're now running things online, right? You collect a lot of data, you want to say, what's my best estimate of x10? But I have all the measurement up to y100, that's fine.
Is this better than x?
Yes, sure. You have more information, sure. Sometimes this is called smoothing. All right, so this is fine. But we don't use it. I just want to make sure you can generalize my notation. Some students struggle with my definition of here. I'm not sure how much you struggle. PKK, the covariance matrix of xk. So this is, let me say, this by definition, okay, this is the covariance of xk with xk given yk. Yuntian, can you kind of explain this now by reading this formula? What does this mean?
The undetermined matrix of our estimation xk given all measurement up to time k.
Okay, so this guy is y0 all the way to yk, right? That's all the measurement I collect over time. If I see this measurement, you should follow my structure, okay? Or try to follow roughly. If I see this measurement, I still don't know xk for sure. So xk is still random. That randomness has a distribution, right? It's random. For any random variable, I can compute its covariance. Are you with me? For any random variable, I can compute its covariance. This is the covariance of that randomness. What randomness? So the xk given all the capital Yk. Does this even make sense? Yes, it makes sense. So given Yk, capital Yk, your belief about xk changes. It's still random, but the randomness changes. It's like today's temperature of Guangzhou. I tell you, then your belief about today's temperature of Shenzhen will change accordingly. But the updated distribution is defined as xk distribution given yk, and the covariance associated with it is called covariance of xk with xk. All right, so that's this. And this guy is the same thing, given measurement up to k minus 1. Then my belief about xk changes. It's still random, and that randomness has a covariance or lead to a covariance. By definition is this. Okay, you should know low things by hat. Those are the numbers. Okay, you take expectation already. Those become numbers. It's almost the same like a x minus 0 or x minus 1, things like that. Right? The only thing matters is that X is still random, but the randomness is not the original randomness of X. It's the modified randomness after you see Y. Okay, I think that takes some effort for you to understand. And I have simplified notation, which is if I don't have a bar given, that means given the time up, given all the measurement up to the current time, K. So the things I want to try to estimate, the time I want to estimate the state is the same as the time is same as the time step I receive all the measurements. Okay, so these are the same. If I say K minus K, then I need to specify. If these two indexes are different, I need to specify them. Otherwise, I will give PK for shorthand notation. Okay, now we have all the notations. I think we'll derive Kalman filter. All right, I think maybe we should be able to finish after next class. All right, take a break.